Hey, what's up? It is Friday. Happy Friday, April 14th, 2022. Okay, and yeah, hope you're having a good Easter weekend so far. It was a super nice day around where I am, and I am just excited on a Friday night. What other thing to do is there besides do a coding problem? Yeah, well, I could have gone out tonight. I could have done a bunch of other stuff, but the code backend and algorithms, when they call, you just it's you kind of just gotta do them. When you gotta go, you gotta go, right? It's the equivalent, I think. All right, so yeah, today I or tonight I want to do a graph problem, but before I do, let me remind you, welcome to Coding with Shaft. That's this channel. If you like this video, like, subscribe, leave a comment, click the bell icon, do whatever you need to. I try to record a new video every day, a coding video, and hopefully these videos help people out. Um, and yeah, they make me better at talking about algorithms. I know that for sure. Yeah, okay, so let's get on with that. With that being said, so here is a classic problem. It's a graph problem, 1971. Find if path exists in graph. Ignore the fact that there's no articles in this. There's no articles, yeah. Okay, this is an easy problem. I'm gonna like it. It seems like a lot of people like it, and I can see why, and you'll probably see why when you read it. Because it's a nice computer science problem and definitely tests your ability to sigh with the best of them. So let's get on with it. There is a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 inclusive. The edges in the graph are represented as a 2D integer array edges where each edge of I equals u of I, v of I denotes a bidirectional edge between graphs I and vertex v of I. Every pair is connected by at most one edge, and no vertex has an edge to itself. So there's no self edges. Okay, if you've seen in graph theory, self edge is like a loop where the vertex can be referring to itself, and you can technically travel the self edge from a vertex back to itself. There's none of that going on. You want to determine if there's a valid path that exists from vertex source to vertex destination. Given edges and the integers n, source and destination, return true if there is a valid path from source to destination or false otherwise. And here's the example, an example, 0, 1, 2. Okay, these are all connected in this like triangle graph here. N equals 3, edges 0, 1, etc. Source 0, destination 2. So from 2 to 0, there are two paths, right? 2 to 0, 2, 1, 0, okay? And or 0, 1, 2 and 0, 2. This is a bidirectional graph, right? So this isn't a DAG, or this isn't a directed graph or anything, or a digraph or anything like that. This is graph where you can travel along the edges in either direction, each edge in either direction. Okay, so the answer here is that there are two paths, okay? And remember again, find if path exists in a graph, okay? So if path exists in a graph, that's easy. You don't have to even provide the path. You just need to tell whether it exists or not, okay? So it makes this problem easier, and so on and so forth. This is a graph with two connected components, and in each connected component, you can see, so the question asks from source 0 on this graph to destination 5 on this graph. Does a path exist? And no, it doesn't. And the reason you know that is because these are two disconnected, two connected components are disconnected from each other, okay? They're mutually exclusive in terms of graph space, okay? So there's no duplicate edges either. Okay, great. So you can't have like a bone-shaped thing here where there's one edge and another edge and you can go back and forth. That's another thing in a multi-graph, right, in computer science. Okay, so with that being said, we know the gist of the problem, so let's get on with it, trying to solve it. I think this shouldn't be too difficult. So basically what we want to do, so I'm going to solve this using DFS. I'm going to do a simple technique on this. There are more advanced methods, right, to search a graph, but a DFS sounds like a good way to me. And so what does that mean? So basically, the idea is to search at the source node, because you're given the source node from vertex 0, for example, here, and then try to search to the destination node. So how do you do that? So in a depth first search, which you've seen me do in trees, you basically take a node and you can recursively refer to nodes that are connected to that node. Okay, in a tree, trees are easy because they're graphs that don't have any cycles by definition. And if these were trees, or just if this was a forest, which is this would be a disconnected tree here, then you could just simply do the kind of DFS node searching we've been doing before. But in this case, we'll probably have to do a little bit of more complicated DFS, but either way. So one thing I like to do, and this is something you don't have to do, and you can make this a lot easier on yourself, but I like to represent the graph. This is an edge list. Okay, I like to represent the graph in approximately an adjacency list structure. So this does take some cycles of time. So it's not really the most efficient way of doing things, but it's a start. Okay, the point of this is to explain how this is done. So let's see. Visited equals new boolean and plus 1. Okay, my make graph function is going to turn this edge list into a adjacency list. Okay, and remember what an adjacency list is versus an edge list. Okay, an adjacency list is an edge list basically is where you have all the edges in the graph. So there's an edge from 0 to 1, there's an edge from 1 to 2, and then there's an edge from 2 to 0. An adjacency list is a different representation. So an adjacency list is basically a representation where you have your graph looking like graph of 1, 0 equals nodes connected to 0. Graph of 1 equals nodes connected to 1, and so on and so forth, all the way to n, graph of n. So to me this is easier because I'm looking for, I want to be able to refer to a vertex and everything connected to it so I can decide where to traverse next in this graph. So for now, so that's basically why it's called adjacency list. It's a list of everything adjacent to each element in the graph, each node. Okay, so visit. So I'm going to have a function that actually does the visitation. And then once visit occurs, right, this thing that I'm passing in here, visited here, I've defined this as a Boolean array. Visited is going to check whether the node in destination has been visited after the call to this visit function. So return visited of destination. Okay, so basically that's that's what's, again, that's easy. It's done, folks. No, not at all. That's the kernel function. Now we have to define our helper functions, right? So you see I made this hash set here of this array of hash sets, right? So this is an array of hash sets, okay? Just to get this notation clear as to what I'm doing. And this is again in Java, so, but might be a little verbose, but it's okay, bear with me. So hit make graph int. I'm gonna pass into this make graph the edge list, and then I'm gonna pass the list int n. So I'm passing in the total number of vertices and the edge list, and the first thing I do is initialize my empty graph. So my empty adjacency list. So that's this. And just remember the words adjacency list. Okay, it's a list of things adjacent, a list of nodes adjacent to each node in the graph. Okay, that's all it is. Some people don't like that word because it sounds too mathy. Well, I'm here to tell you that, you just have to think about these words for a bit, and then they'll be more um, accessible to you. Okay, so graph. This is what I'm here. All I'm doing in this loop is initializing my hash sets. Okay, here you go. Okay, just remember this here. Okay, and each element, the ith node, will be a whole new set of integers, where each integer represents all the nodes attached to it. Okay, second is for now that we have that, I'm going to do the work of converting the adjacency list, the edge list into the adjacency list. And some of you are no doubt saying that, oh, well, what is the point of all this? You can simply search the edge list, using an algorithm. And yeah, sure, I could do that, but I want to, again, be demonstrative of how this works. And I think the adjacency list generally, when applicable and when easy to implement, and in this case I think it is, it makes the most sense. Okay, and is the right answer. So here we go. This is what I've taken the graph, okay, and in the loop I've set this destination. I've obtained the hash set associated with the edge, the graph of the vertex at the ith edge, because we're iterating through the edge list, right? Okay, and this here is the start of each edge. Okay, now, so remember, edges, right? Edges has two elements. Edges has a start. The ith edge basically 0 equal is the start of edge. Edges I1 equals end of edge. Okay, and remember, they're bidirectional components, so when you're connecting the graph, you have to connect both of those together, not just one. If this was a directed graph, you could just connect one, but that's not the case here. So, okay, so now that I've added one edge, now I'm going to assign the edge to this new list of things that are adjacent to it, okay? And if this doesn't make sense, I'll go over it in a second, but it should hopefully be straightforward to you. Okay, I sensed the flash logo, yeah, I knew it. Okay, and dest.add edges by 0 graph edges 1 equals dest. Okay, then we want to return the graph, because this function was just solely created to build the graph. And now we are simply returning it. Okay, so now the final function here is my visit function. So this is what happens when we actually visit any node in the graph. Okay, but before I get to that, let's explain what's happened here. Okay, because this bears repeating. So the first part is init adjacency lists for each vertex I. All right, adjacency lists are the vertices that are closest to that one, that are attached to that one graph, not closest, attached to the one graph. Okay, for I equals 0, I less than edges.length, this I plus plus. Here, all I'm saying is that each adjacency list, the adjacency list of each edge, is start and end vertex, is going to get updated with the end and start of that, depending on where it is. So if you have one here, an edge to A to B, the list of A equals B, and list of B equals A. I guess this is the best thing. Now these two are connected together because, for example, 3 connects this 3 is in 5's adjacency list and 5 is in 3's adjacency list. So if I did 3, I'd get 5, and in this case 4. If I did 4, I'd get 3 and 5 list 5 equals 3 and 4. Okay, so again, these are the elements adjacent. Okay, and so that is something just fell. Don't worry about it. And that is what we're doing here programmatically. Okay, so now what are we going to do here? Okay, now that we have this going on, we're going to visit this next integer. We're going to visit each element now that we've created the graph. Okay, so how do I visit each element? Okay, that requires that I create visited. That requires that I create a recursive function to do the visitation. Okay, and I'll go over that in a second. This isn't too bad. Okay, visit graph v visited. Okay, this is the visit function. So let's go over what's going on here. I send in my graph, which is my adjacency lists, and I have next is basically where I'm going to start. Okay, I've started somewhere, and I've been giving a source. Notice I'm not passing the destination into here, and there's a reason for that. And the visited array is the array that I'm going to be passing down recursively throughout all the functions calls in the call stack to check whether the element has been visited, and to visit the element first of all, and then check whether each subsequent call has created more visited elements. And if they haven't been visited, then I visit each element. If they have been visited, then there's no reason in continuing on with that stack anymore, because we know we've already got to a cycle, or we don't have anything more adjacent to visit. Okay, so that, and just so you can understand how this works, if visit is called at 3, right, then 3 will visit 4 and 5. Okay, 3 is marked as visited, then 5 is we'll check whether 4 and 3 has been visited or not. So 5 is now visited. 5 will then visit 4, right? Because 3 will visit 5, then visit 4, right? 3 does not visit 5, then visit 4 here, because this is the difference between a breadth first and a depth first search. In this depth first search, 3 visits 5, then 5 visits 4. We go the depth of the graph, right? In a breadth first search, again, 3 would visit 5, and 3 would visit 4 before continuing on the graph. And that can be best seen with larger graphs and some kind of like visualization. Okay, but that's basically what this is doing. So this is basically going different paths throughout the graph. Okay, let's see how this works. I believe this is it. I'm sure I have some error. Okay, hash set integer graph. Sorry, there's lots of noise in my area today. 36. Okay, and cannot find line 10 equals new. Okay, I do Kotlin programming too, so sometimes I forgot the new keyword. And on 22 we have edges. not eggs. Eggs. All right, true. Okay, that was accepted. Now let's see. And there you go. That was accepted. Okay. Now, obviously, I've done this problem before. I do refer to my code that I've written on the discussion to make sure I don't make any mistakes. So that's just something to note. And yeah, that's it. So basically, again, it's not very fast, right? There are faster ways of doing this. For example, if you look into union find, or there's even algorithms that don't even use one of the standard graphical techniques. You can use a hash map. But anyway, this is a good depth first traversal of this graph. And cool. So that was it, a long video. Thanks for watching. I'll see you next time.